All right, so today we're talking about 11. We're jumping ahead one section, 11.5. So we're going to talk about the volume of prisms and cylinders. First off, let's talk about what we mean when we say volume. When we're talking about the volume of something, what are we talking about? So we're talking about something that's three-dimensional, and we're talking about how much space is inside the shape. So the space inside. And we could also think of it in terms of how much space a solid thing takes up. How much space does it take up? Kind of the same thing. Takes up, occupies, how much space a solid occupies. So before we get to our formulas for our volume of prisms and cylinders is pretty easy. I want to talk about something that lets us find the volume of any kind of prism and any kind of cylinder, not just a right prism or a right cylinder. So we don't have to worry about whether it's a right cylinder or an oblique cylinder, a right prism or an oblique prism. This lets us find the volume of anything, and that is called Cavalieri's principle. Cavalieri's principle tells us that if two solids have the same cross sections, and remember, cross-section just means the shape that we get when we slice it with a plane. Two cross-sections at the same height for every height. Then they have the same volume. So let me show you what Cavalieri's principle is telling us. Here is my solid. This stack of books is my solid. The cross-section of a stack of books, if I slice it parallel to the table, the cross-section is a rectangle, the shape of the book. Does that solid that I got when I shifted those books over have different cross-section? Have I changed the height of the books? The books are at the same height. They have the same cross-section. Do the books take up any different amount of space because I shifted them sideways? No? So the volume of this solid, that stack of books, is the same as the volume of that stack of books slid sideways. Well, the stack of books slid sideways is like an oblique prism. And the stack straight up is like a right prism. They have the same volume. I could rearrange the books any way I wanted, sliding one way, one the other way, and those solids are going to have the same volume because the books, I'm not changing the volume of the books. At each height, they have the same cross section. So I could rearrange these in any way that I wanted, and I would get the same volume. So that's what Cavalieri's principle is telling us. We slice their solid into tiny little thin slices, If the cross section is the same, that's telling us the shape's not changing as we move up or down. The shape is still the shape of the book. The shape's not changing. The volume doesn't change. So our volume formulas work for oblique prisms, oblique cylinders. It'll turn out to work for oblique cones and oblique pyramids as well because of Cavalieri's principle. So that lets us say for our formulas for volume that they work for any prism or any cylinder. So let's write our formula. Cavalieri came up with this idea, and I'll talk a little bit more about Cavalieri's principle in a little bit because it relates to something that we do a lot in math. All right, so let's talk about our formula. The volume of any prism can be an oblique prism, can be a right prism. Very easy formula. Volume equals the area of the base times the height. And our units are cubed for volume, units cubed. B is the area of the base, and H equals our height. And this is the height of the prism. So nice easy formula. A couple of places where students make mistakes. Remember that capital B means the area of the base. Sometimes students want to think B just means the segment that's at the bottom. Remember, capital B is the area of the base.
And the base means is each kind of prism.
Right. We name the prism, the type of prism it is depends on the shape of the base. So the area of the base depends on what shape the base is. Triangle, we have to find the area of a triangle. It's trapezoid, we have to find the area of a trapezoid. It's pentagon, etc., etc. All right, so let's look at a couple of examples. So here is my shape. And I know my drawings don't always turn out perfectly, but so there's my shape, and we're going to say this side is 6 meters, this side is 5 meters, and this side is 12 meters. And we want to find the volume. So what do we want to call the base here? Which side do we want to call the base? How about let's call this side the base. So this would be a rectangular prism, which is a fancy way of saying what? A box. This is a box. So our volume is the area of the base. Area of the base is 6 times 5, or 30 square meters. The height, what's the height of this prism? 12 meters. So our volume is 30 times 12, which is 360 square meters. What's another way for a box, what's another way we've thought of finding the volume of a box? Length times width times height. Length times width times height.
Wait, isn't the volume
Cubed, yes. Because I have a meter squared here and another meters, that gives me meters. Thank you. So our volume, for a box, we've thought of the volume as the length times width times height. Well, the length is 6, and the width is 5. So the length times the width is the area of the base. So length times width times height is the same thing as saying the area of the base times the height. Just a different way of saying it. We had to find the length times the width to find the area of the base. So the length times width is the area of the base. So those formulas are really the same thing. They're not different formulas. They're the exact same formulas. This one only works for a box, a rectangular prism. Area of the base times the height works for any prism. All right, questions on that example? All right, let's look at one where we need to do a little more work. Because not all the shapes that we're going to talk about will be nice boxes. And I was going to go back. This is a big box, 6 meters by 5 meters by 12 meters. It's a pretty good sized box. Yeah, for refrigerator maybe, small refrigerator, big refrigerator maybe. All right, so here is our shape. So we have 6 inches, 6 inches, 6 inches, and 10 inches. And we want to find the volume. All right, so what kind of shape do we have? Triangular prism. Our base is a triangle. Let's draw a picture of the base. So here's my base. And let's start our little list over here. What is the height of the prism? 10 inches. So we need that to plug into our formula. We need the area of the base. How do we find the area of this triangle? Base times height divided by 2. So we have the base of our triangle is, we know that our area of our triangle is base times height divided by 2. We know the base of the triangle is 6. We need the height. So let's draw the height in. Here's the height of my triangle. There's the height. How do we find the height? We could use the Pythagorean theorem. So, because what does this side do to the base of the triangle? Cuts it in half. So this little piece is 3. We can use the Pythagorean theorem. That would always work. But if we remember, this is what kind of triangle with all the sides the same? Equilateral. The angles in an equilateral triangle are 60 degrees. So that's 60 degrees. What does that make this angle? 30 degrees. This is a 30, 60, 90 triangle. We talked about this when we talked about finding the area of polygons. So if this side is 3, we're going from the short side to the long side of the 30, 60, 90 triangle to find the height. How do we go from the short to the long? Multiply by the square root of 3. So for the triangle, the base equals 6, the height equals 3 times the square root of 3. And the area of the base is 1/2 the base, 6 times 3 square root 3. Half of 6 is 3 times 3 is 9. Square root 3 square inches. So area of our base is 9 square root 3 inches squared. And I get my volume is 9 square root 3 times 10, which is 90 square root 3 cubic inches. So this would be my exact answer, my answer in simple radical form. So we had to remember, for this problem, we had to remember that to find the area of an equilateral triangle, we can divide it into two 30, 60, 90. And then we used our 30, 60, 90 rules to find it. Questions there? So our base is the key, and usually in these kinds of problems, finding the area of the base is one of the, I'm not going to say the hard part, but that's probably one of the the part that we have to put more work into, is finding the area of the base. That's the key. All right, let's talk about cylinders. The volume of any cylinder. And I say any because Cavalieri's principle works for cylinders as well. And let me show you, I was so excited when I realized that I could do this. Here's my cylinder. The cross sections are the little rings here. Cross sections haven't changed. Same height, same cross section. Volume of this shape is the same as the volume of the cylinder, like Cavalieri's principle. Volume of this shape is the same as the volume of the cylinder because my cross sections are still the same. The cross sections are still circles. It hasn't changed up or down. So no matter how I move this slinky around, Cavalieri's principle tells me that the volume of that shape is the same as the volume of the original. So a slinky lets us think about Cavalieri's principle. So if I put water in here, if this were waterproof, and I put water inside the slinky, it had a bottom, and I slid it around, moved it around, the water, it would hold the exact same amount of water as if I put it in like this. So slinky is a nice way to think about Cavalieri's principle. You get this really complicated shape, and its volume is the same as the volume of the original cylinder. And that idea of slicing our shape into a bunch of little tiny thin little strips, if you go further in math and you study calculus, that's one of the key ideas in calculus, is to divide a shape, to divide an area, divide things into tiny little pieces and add all the little pieces up. So Cavalieri was working on an idea that's related to what one of the most important ideas in calculus is dividing things into tiny little pieces and then thinking about those tiny little pieces and adding them up. Kind of a nice preview to ideas that you'll talk about later on. All right, so the volume of a cylinder, exactly like a prism. That's why we're talking about them together. Our surface area formulas were the same. Our volume formula is the same. The volume equals the area of the base times the height. I'm going to draw a cylinder over here. So here's my cylinder. What is the base of the cylinder? Circle, right? Our base is a circle. So the area of the base is the area of this circle. And what was that, right? Pi r squared. And units cubed. So R is, let's say B equals area of the base, which is equal to pi r squared. R equals the radius of the base, and h equals the height. So because our base is a circle, the area of our base for a cylinder is always pi r squared. So that makes cylinders, working with cylinders, a little easier because our area of our base is always just pi r squared. But it's the exact same formula, pi r squared h. We can use this for an oblique cylinder or a right cylinder. And we could actually use it for, like we talked about with the slinky, some shape that'll look like this. As long as the base, the areas of the base were the same and the heights were the same, and our cross section were the same, I could deform this cylinder and get a shape like that, and we could use the same formula to find the volume. All right, questions on our formula? So our volume formula is usually a lot easier than our surface area formulas. All right, let's do an easy example first, and then we'll do one that's takes a little more work. So here's our cylinder. And we want to find the volume of this thing. So we need the area of the base, so we need our radius. So what's the radius of our cylinder? Six. The diameter is 12, so the radius is 6 meters. The height is 14 meters. So plug those into our formula. Our volume equals pi times 6 squared times 14. And let's say find our volume in terms of pi. In terms of pi. So this is going to be, our volume is going to be 36 times pi times 14. 36 times 14 is 504 pi meters cubed. 504 pi meters cubed. So that one was nice. Find the radius, find the height, plug it into our formula. Questions there? All right, let's do one more example that takes a little more work. So here's my shape. Draw this a little better. There we go. Over there. And this is 11 inches, 6 inches, 12 inches, and this whole thing is 17 inches tall. And we want to find the volume. So what is this shape? Rectangle with half a cylinder on top. So we don't have a formula for the volume of a lunchbox. So we need to figure out what formulas that turn it into shapes that we know how to work with. So this looks like a prism with a half a cylinder on top. So here's my, let me redraw this. Here's my prism. and my dimensions, my scale is not going to be exactly the same. And that's 6, 11, and 12. And then we have a half a cylinder, like so. And how long is this side of the half cylinder? Same as this, because it fits right on top. So that's 11. Do we know the radius of the cylinder? What's the radius? 17. The total height, and this part is 12, so that leaves 5 for our radius. So that's 5. And we find the volumes of each of these and add them together. The way I drew my picture is impossible, isn't it?
Yeah.
So yeah, if this was 6 inches, that would be 6 inches. So let's see. So I made these numbers up. So I made my height impossible. So this is 6 inches. This would have to be right. So this would have to be 3. So we'd have to have this be that. So that wouldn't work either because I said that was 12. So that's 11. So let's say, and this is 3. So 11 minus 3 is 9. There, that'll work, right? Uh, 11 minus 3 is 8. Yes. Nice catch, Olivia. Nobody in my other class noticed.
Oh.
So the diameter of the circle has to be 6 inches. So the radius has to be 3, and we have 11 inches there, and we have 3 inches there. Okay. Now we're set. Now we made a shape that actually works. All right, so now we're going to find the volume of the prism. The volume of the prism is, we're going to say the area of the base for the prism. Which side do you want to call the base here? Doesn't matter. We just need to do 6 times 8 times 11. So 6 times 8 times 11, let me calculate that out. We get 88. 88 times 6. 528 cubic inches. And for the half cylinder, our volume is going to be the volume of the entire cylinder. We'll divide that by 2. So I'm going to say 1/2 pi. Our radius is 3, and our height is 11. So we're going to get pi times 3 squared times 11. And we'll do this to the nearest 10th, I guess. So we get 99 pi divided by 2. 3 squared is 9 times 11 is 99. Multiply that by pi and divide by 2. So this is 99 pi divided by 2. So 99 divided by 2, and multiply that by pi, and I get about 155.51. So I'm just going to say 5 inches cubed. So the total volume now is 528 plus 155.5 inches cubed, and when I add those together, I get 683.5. Inches cubed. So I had originally made an impossible shape. This one. Yes. And Olivia figured it out. Sensor help. So the radius and the height didn't work out to get the way that I set it up. Yeah. All right, questions there? So if we have an odd shape, we need to figure out how we can divide it into shapes that are more familiar, that we know the formulas for. And then we calculate our volume from there.
Did you call them composite shapes when you started?
I did not. The book calls them composite shapes. I just think of them as odd shaped things. How can I divide it up into something that I know how to work with? This also reminds me of playing with blocks with my son. Stacking the pieces, because they always make them so they fit. All right. Homework. What day is it? It's block day. Page 722, number 6 through 34 even, and 38.